What if I told you that one of the biggest breakthroughs for the future of quantum computing wasn't found in some billion-dollar super collider, but was actually hiding in plain sight, inside a simple beam of light? Yeah, let's get into it.
So, to really get why this discovery is such a massive deal, we first have to understand the core problem with all quantum technology. It's this classic story, really, of incredible, world-changing power and one single critical weakness.
You know, on one side, you've got this amazing promise. Computers so powerful they could solve problems we can't even properly imagine today, and communication that is physically impossible to hack. But on the other side, the information itself is just unbelievably delicate. Seriously, it's like trying to build the most intricate, perfect sandcastle right where the waves crash. The tiniest little disturbance, a stray magnetic field, a small vibration, and poof, your entire calculation is gone. That fragility has been the biggest roadblock for a long, long time.
So where on earth did the solution come from? Well, it came from looking much, much closer at the everyday tools that quantum scientists have been using for years. Let's break down the two key components that make this story work.
Okay, first up is a process with a real mouthful of a name: spontaneous parametric down conversion. Let's just call it SPDC. All you need to know is that this thing is basically the workhorse of any quantum optics lab. It's a totally standard routine method for taking one particle of light, a photon, and splitting it into two new photons that are quantumly linked up. We call that entangled. This is happening in labs all over the world right now. It's just standard procedure.
Now, the second piece of this puzzle is a property of light called orbital angular momentum, or OAM. A really simple way to think about it is that a beam of light isn't just a straight arrow. It can actually have a shape. OAM is the twist in that shape, almost like its wavefront is spiraling forward like a corkscrew or a spiral staircase. This is a huge deal because it means light can carry information not just in its color or its brightness, but in its physical twisting shape.
Okay, so we've got our standard tools, and this is where the story gets really good. A team of researchers from the University of the Witwatersrand and Huzhou University decided to take a much closer look at that totally normal SPDC process. But they focused specifically on the shape of the entangled light it was creating.
And they weren't using some brand new radical piece of equipment. Nope, they were looking at the exact same entangled photons everyone else was making. But when they analyzed their structure, their physical shape, they found this hidden property, a secret layer of organization that somehow no one had ever noticed before.
And what they found was just staggering. These weren't just simple little patterns. These hidden structures existed across, get this, 48 dimensions. 48. That is the highest level of topology ever observed in any physical system. I mean, we're not talking about just up, down, left, right. This is a level of complexity that is genuinely hard to wrap your head around.
And it wasn't just one amazing structure. The team identified over 17,000 unique, distinct topological signatures. It's like they cracked open a single grain of sand and discovered it contained an entire uncharted universe of patterns inside. Absolutely incredible. Now here is the most crucial part. As one of the researchers, Pedro Ornelas, put it, you get this topology for free. This isn't something you have to painstakingly build or engineer. These incredibly complex structures are just a natural, built-in property of the entangled light itself. It was always there, the whole time, just waiting for somebody to finally look in the right way. And this just beautifully shows the power of theoretical physics. The lead author, Professor Robert DeMello Koch, explained that really abstract ideas from quantum field theory basically handed them a treasure map. The theory predicted these structures should exist and told the experimental team exactly where to point their instruments. And when they looked, yep, there it was. Okay, so we've got these thousands of ridiculously complex, high-dimensional patterns hiding in entangled light. So what? What are they good for? Well, it turns out they are the perfect, elegant solution to that fragility problem we talked about at the very beginning. The secret is in that word topology. Basically, topology is the study of shapes that stay the same even when you stretch them, bend them, or twist them around. Think about it like this. A donut and a coffee mug are topologically the same thing because they both have one hole. You could, in theory, squish and mold a clay mug into a donut shape without ever tearing it. That property, the one hole, is robust. It's stable. It's like how a knot in a rope is still a knot, no matter how much you shake that rope around. And that inherent robustness is the key. So how does this give us a new way to protect quantum information? Well, the whole process is just beautifully simple.
Step 1, you create your entangled photons using the same old standard SPDC method. Step 2, you encode your information, your data, into one of these super robust topological structures. And finally, because that structure is like an unbreakable knot, it stays stable, it resists all that outside noise, your precious quantum information is protected by the fundamental shape of light itself.
And you know what makes this even more powerful? It's way simpler than anyone thought possible. Professor Andrew Forbes points out that before this, everyone assumed you need to combine at least 2 different properties of light to create these kinds of protective structures. But their discovery shows you only need one, that twist, the orbital angular momentum. And since OAM is already naturally high-dimensional, it means the protective knots you can create are incredibly complex and powerful right out of the box.
So, let's pull all of this together. What does this amazing discovery, published in the journal Nature Communications, really mean for the future of quantum technology?
So, what are the big takeaways here? Well, first, we now have a brand new way to encode quantum information that is naturally tough and resistant to noise. Second, and this is huge, it uses existing standard lab equipment. This means researchers anywhere in the world can start exploring this right now. It basically overcomes one of the biggest hurdles that was holding back practical quantum technologies, and it opens up all these new avenues for building the stable quantum computers and secure quantum networks of the future.
It's just an incredible reminder, isn't it? Sometimes the biggest discoveries aren't about building something new and complicated, but about learning to see the world we already have in a completely new light. It really makes you wonder, what other fundamental secrets about how the universe works are hiding in places we look every single day, just waiting for someone to ask the right question?